Hodgkin and Huxley chose to work with the nerve from a giant squid because, as you can see here, it's a naked eye object. Um, it's the radius of that axon is actually around a millimeter or so. So they were able to do all kinds of things. One of the things they did is they experimented with, well, let's just maintain the axon. Let's forget the ends of the nerve, and let's just look at the properties of the axon. And they looked at what happens if we simply replace the fluid inside the axon with an ionic fluid, and they find um, that that the fluid inside the axon was not what was important. That it was the membrane itself that was important. And after they worked with it for a while, they discovered that, oh, what's going on is either sodium or potassium is flowing back and forth through the axon. And the time scales for these are very different, right? And they, so if you look at this leakage term, the current going through the membrane from outside to inside, they now wrote it out as, okay, I've got a sodium piece, and I've got a potassium piece, and then I've got this miscellaneous piece. And we know from the Nernst equation about what our voltages, our equilibrium voltages should be, right? So the leakage current they're saying is going to be the conductivity per square meter times the difference of the voltage from equilibrium, right? So equilibrium is defined by the Nernst equation. Um, and so this should tell you a good bit about how both sodium and potassium are flowing through the membrane. And these symbols here indicate that this is a variable gate of some sort and not just a standard resistance. And then the leakage current over here, that's just a leakage current of miscellaneous stuff that has nothing to do with the conduction of the nerve. Um, so if they look at the conductance for the two different ions, for sodium and potassium, over the length of a pulse, so you send a pulse through, and what happens? You can see here the conductivity for sodium shoots up very quickly and it decays very slowly. And the conductivity for potassium slowly rises. Well, when you think conductivity, you should really think, oh, this is kind of like, for a given voltage, it's kind of like current, right? So the current due to sodium shoots up and then decays. And then the current for potassium due to potassium slowly grows over time. All right. So this the conductivities of these two uh, tells you what's going on with these as we look at what's going on with these ions in trying to balance out the fact that we've changed the voltage in the axon. All right. Well, they looked at this very carefully and trying to figure out, okay, what's going on here. Um, Clearly, there are two processes going on with sodium. There appears to be only one going on uh, with potassium. And so, oh, let me back up. Um, and so they modeled out the potassium first, and they got a good fit for potassium. And there's this function and this function is the solution to a differential equation. You can only solve that differential equation using computers, yada, yada, yada. Okay. Um, the big thing to think of is this function is called the potassium gate. It ranges from 0 to 1, right? If it's 0, no potassium flowing. If it's 1, potassium's flowing. And so the potassium conductance is given by this. Um, and what you need to keep in mind in infinity is the potassium conductance way out at, after you've reached some steady state. So the general shape of this is what's important. Um, and if you look at time scales for things, potassium has a slight different time scale. It's not constant. Time scale slowly changes. If you look at sodium, there are clearly two processes going on with sodium. And they believe this because there's one that's a rising process and another that's a decaying process. And if you look at this, this looks a lot like an exponential decay. And so what they proposed as a model was a activation gate, M. So M is turning on, right? And an inactivation gate, H, which is turning off. And so when they fit it to the model, it was M cubed times H. And you think over here we had to the over here we had to the fourth. Well, here we still have to the fourth in some level because we got M cubed times H. The form of these are very similar to this one with different constants. And again, you have to use a computer to try and solve all this, which is why you see computer code in the book. And you know, the other thing that happens here is since H lets things get going, H is the activation gate. One of the important things is experimentally, it takes several milliseconds after this process has gone on for H to be able to generate another action potential. And that's a refractory period. So pulse goes down the nerve, and then there's got to be a little rest before another pulse can go. All right, that's it for what's happening with potassium and sodium. I know it looks very complicated, and there are a lot of details in the background here, but basically the general gist is, as a pulse goes through, sodium conductance rises, potassium conductance rises, and then begins to fall.